To the second presentation today, which is the speaker is Luis João Braga. He studied computer science and focuses on artificial intelligence applied to infinite infrastructure. He has a degree in IT and is a member of several scientific associations such as Internet Societies, SEM, IEEE, and others. So welcome, Luis João. Structure for the acquisition, representation, and use of knowledge, learning, and collaboration between START multi-agent systems in the Internet Infrastructure Domain, SKAU.
Acá con este va la siguiente.
Boas tardes. Eu vou apresentar, na realidade, um projeto de pesquisa que tem mais ou menos 10 anos que nós estamos trabalhando nele. E, mais recentemente, ele está ficando um pouco mais elaborado do que a gente imaginava. E, por enquanto, essas três pessoas envolvidas aí, que é a professora Itana da UFABC e o Percival Henriques da Unicap, desculpe, lá de Pernambuco, a Universidade Católica de Pernambuco. Esse projeto, na realidade, é uma arquitetura de agentes para trabalhar em um domínio restrito. A proposta é a arquitetura e o ambiente necessário para que essa arquitetura de agentes possa funcionar adequadamente dentro de um domínio restrito. Então, vou começar só para a gente se entender melhor na definição sobre agentes. Vou usar essa definição clássica aí do Russell Novick, desse livro aí, que na realidade é uma definição de 1995. Quer dizer, ela é bem antiga, mas a gente está se falando há muitos anos. A estrutura que ele propõe para a gente é essa aí, quer dizer, definindo que um agente é algo que tem percepção de seu ambiente, quer dizer, ele entende o ambiente através de sensores ou de algum mecanismo que permite que ele entenda o ambiente e atua sobre esse ambiente através do que a gente chama de efetores. Às vezes, um agente na realidade, um agente é um programa de computador e que, às vezes, ele não precisa nada disso. Ele basta ser um programa para ele agir dentro desse ambiente.
So this becomes more effective when this has computing tools available. Tools in general terms nowadays, the AI tools, and there are quite a number of these available, can be used to solve algorithms, even more sophisticated algorithms. We have the multimodal large language models. The LLMs are the multimodal options we have out there in the market. And these are for example, ChatGPT and many other tools of this kind. But even more important is what we call ontologies. Ontologies are special databases with the main goal of making knowledge available to the agents. These are thoughts, or it is knowledge that we have as human beings, and to transform this knowledge so that the agents can use it. These ontologies that Alvaro also referred to a while ago work with a type of mathematical logic that is called description logic and first order logic. It has some interesting features. It has interesting features for descriptions. One of these is that it can decide, it is decidable. If I make a representation in the description logic, it means that this is true or false. So it can make decisions based on this. Let me give you an example. This is how we can represent knowledge through this graph, this knowledge graph. Let us assume that IXBR, which is managed by NICBR. NICBR is the operational branch of CGI-BR. Galvão, who allowed me to mention his name, is a person. Galvão works for Ajax.br. So how can I represent this knowledge with knowledge graphs? Alvaro also referred to this in his presentation. So this is how we can represent this. IX.br is administered by NICBR, and this is the operational branch of CGI.br. Galvão works for IXBR. Galvão is a person. Now this graphic representation can be translated using ontology through a language which is the description language called OWL. And this was proposed by W36, and it is used quite a lot. Now assume that you have a computing agent 01, and it is using this ontology on IAX.br. AC01, which is the agent, could it respond to this question? Does Galvão work for NICBR? This information that Galvão works for NICBR is not clear in this graph, but it is implicit there, because if he works for IX.br and IX.br is managed by NIC.br, then it could include that AC01 works for NIC.br, so the agent could reach that conclusion. So that is possible because the explicit knowledge, which is what we have on the graph, can be concluded through the logic inference. This is a resource of the logical language, so it can conclude on certain types of knowledge. So we can start to think about the different types of agent types. We have the first agent is a computational agent. This is very simple. And if the definition follows the definition of Russell Norwick that we had at the beginning, the one I shared with you at the beginning.
It can be a little bit more developed using IT tools and databases and the knowledge databases, that is the ontologies. And there we say that the agent is autonomous, and its autonomy is closely related to the capacity or the need of the human beings to intervene with the agent. It's more autonomous to the extent that there is more activity of the human beings on it. It's the so-called, it's what we call the smart. So it seems as if it were a smart quote-unquote being. So we have the AI agents, more recent, that in addition to the resources that the autonomous agent already has, it has the LLMs and the AI tools available. All these agents can be put together in a network and have a similar structure as we presented, with the feeling that the internet does not need to be a full mesh architecture. It suffices with just have some interconnections to be able to talk with all of them. Here we have a simplified network with a network of agents, with agents of different types, and using additional resources that are available for them to get better. And based on this definition, we did an architecture proposal. That proposal is divided into 4 layers. And I'll spare you the details about the structure, because there's a document that I wanted to show you at the end that describes exactly each component. But there are 4 layers, and each one has its own name. Layer 1 has one single agent that controls everything. Nobody comes in or out without this gatekeeper. Then the second one is the layer of agents that we called as specialized. Then we have a huge layer that are the so-called colony, and finally another huge one too that are the auxiliary agents. Now, the best way we can facilitate the understanding of all this is seeing how its implementation gets represented. Each point is an agent. In layer 1 we have the control agent, that is, it's a gatekeeper. Nobody comes in or out without its supervision. Then we have the rest of the agents that provide support for the activities required for the model to work in a certain domain or environment. Layer 4, for instance, can be established and the process can be repeated, the process that is shown in the 4 layers indefinitely. So it can grow as much as you need it to. It's a network architecture that is it is supervised, because the agent that controls layer 1 oversees everything. That is, things only happen under its command. And this proposal, this is something that we proposed in 2015. This is a document that was presented in the WPEIT, that is the pre-ETF associated to the Brazilian IT meeting. So we completed a drill to see whether the structure was working well. And the IRR, that it's a structure, I don't know whether you all know it, where we establish how it works, or what the objects are in the autonomous system. And it registers all the objects in a server, and the server distributes the information. It all goes to the internet, and there are tools essentially to access an important server. That is where almost everything is focused, and it is the RADB. The IRR is an interesting thing. It's a very well thought structure. However, it has its challenges because the autonomous system administrators do not always update the objects that are usually used in IRR. So, as a consequence, and given the human failures, the IRRs have a bad reputation. In this example, for instance, we use our agent infrastructure to provide it for IRR. There's no human intervention. The agents create the objects, they update them, and they always keep everything updated through the access to the different components of the autonomous system that I'll show you right now. This case study confirmed that the architecture works. So as a result, we decided to go forward with the project. The idea, well, the assumption is that, well, this internet infrastructure that is formed by ASs, by autonomous systems. So A2RD, that is the name, is the way we call our architecture. Each autonomous system might have, or might or not, a set of agents, such as the ones that we have here in our architecture, and they relate to each other. And this one of the issues that was mentioned lately is that the agents in this structure I was saying the agents in this structure that we imagine, they need to understand each other. They need to be able to relate with each other and to work jointly. Each A2RD of each autonomous system needs to talk with another A2RD. So we created a proposal with a system that is based on blockchain, where the agents, that is the A2RD structure, as we call it, that is present in each of the autonomous systems, not necessarily in all of them, but in those where it's implemented and where it's present, they are going to talk to each other, they're going to understand each other with a blockchain structure, and whenever necessary, they're even going to relate with a human being. So this structure was built using blocks. The blocks have this architecture. They're in a position in a chain. All the components are important, but there's a very important component that I'm going to discuss now, that is DOI. It's a second in a row. It's the identity of the agent that owns the block. That is, all the agents in our architecture have an ID. That is the DOI type. It's the digital I don't remember the word, but something in the middle, and then identification. So they are used a lot in scientific papers. The big advantage is that we managed to identify who the owner of that a DOI that was identified, and a number of very precise data. Here you have the example. I'll spare you the details. And here, using when with information of the IRR objects, and it's more or less like this. The big advantage of this blockchain advantage is the structure data that is used in the blockchain. It's an inverted list, guaranteeing that data is secure. That is, if anybody makes an attempt to change it, to alter anything, it's impossible, because the structure will look funny and nobody will accept it as such. So, given all this, we need an environment where the agents can work. The environments, the so-called SCAO, you start with the agents or the structures of architecture, using the mechanism for collaboration with a blockchain and a blockchain. And we'll need a set of knowledge. So the knowledge base is actually the most important thing in our proposal, and with a mechanism of inferences that makes it possible for it to draw conclusions on that knowledge base. That knowledge base, in the case of the proposal of internet infrastructure, needs to be built based on the information that we find in non-structured bases, including, for instance, the AFC repository of IETF, the messages of the working of the IETF task forces, IETF, etc., etc. Road maps, road map manuals, machines, etc. Now, the issue is, how are we going to capture the data and put it in the ontology as knowledge? There's a process that we identify, that we started to create a corpus. For instance, let's assume that I want to capture the acronyms of the RFCs. So you need to take the RFCs in a way such that you may develop an intermediate basis from which you start to draw the acronyms as they appear in the RFCs or the IETF drafts. And that is how we start working with this in a way such that, as a result, we end up having this knowledge base. I won't give you the details, but there's a document that I'm going to share explaining each piece.
There is a mechanism, there's a feedback mechanism in SCAO, in this infrastructure, that keeps a log of the activities and can be used to provide security to the activities that are carried out. and also the things that are being created or manipulated in that environment. We conducted a test. This was in Europe. RIPE gave us an autonomous system to conduct these tests. And at the University of Lisbon, so over a period of time, we did tests using this architecture without details as to how the agents are created and so on. We created 3 different environments. We used Pi. We did this on an IRR base. So this was used to see how this test performed. What is the current status of the project? We finished a systematic review of the bibliography with the aim of projecting, developing, and creating intelligent agents following the machine learning algorithm. In the search terms, we used these databases, Scope, IEEE Explore, ACM, Digital Library, and this is a document that I will be making available to you. We used 36,000 plus proposals for studies. We selected 33 out of all these proposals. These are the references, the 2 documents. If you wish to print, this one is in Portuguese, the other one is in English. And these have to do with the structure that I have described. And all the other documents are related to this project. The part that has to do with the identification of algorithms is the last one. We also prepared a document to explain this proposal. So that would be all. Thank you very much.
Entonces, bueno, un aplauso para él. Si hay...
So if there are any questions, feel free to ask him a question afterwards. And let us very rapidly now go on